Right now, somewhere between Mars and Jupiter, an object named 3I Atlas moving and alive inside. And even some scientists from NASA claimed, yes, this object is alive and moving around Sun too. Something that makes even the most skeptical scientists pause mid-sentence and stare at their monitors with expressions that mix wonder and something closer to fear. Because what they're seeing inside this visitor from beyond our Sun, inside this frozen traveller that's crossed the void between stars, it behaves like something that responds, something that adapts, something that might, in ways we're only beginning to understand, be alive. Before we go deeper into what NASA found, take a moment to subscribe if you haven't already, and tell me in the comments, where in the world are you watching from right now? What time is it there as you're hearing this story? I love knowing that people across every time zone are looking up at the same sky, wondering about the same mysteries. Drop your location and local time below. The story begins not with a dramatic discovery announcement or a press conference at NASA headquarters, but with a subtle anomaly buried in spectroscopic data that a young researcher noticed during what should have been a routine analysis session. It was January 2025, and 3I Atlas had just crossed the orbit of Mars, inbound toward its closest approach to our Sun. The James Webb Space Telescope, that magnificent instrument floating at the second Lagrange point a million miles from Earth, had been tasked with capturing detailed observations of this interstellar visitor. The initial objectives were straightforward, almost boring by cosmic standards. Measure the composition of the coma, the cloud of gas and dust surrounding the nucleus. Track the outgassing patterns as solar heating intensified. Catalogue the spectral signatures of whatever ices were sublimating from the surface. Standard comet science. The kind of work that fills academic papers and advances our understanding of how these objects form around other stars. But the data that came back refused to fit the template. The young researcher, whose name would later appear on one of the most controversial papers in modern astronomy, was examining the infrared readings when she noticed something impossible. The thermal signature from the core of 3I Atlas wasn't uniform. It wasn't the gradually warming sphere you'd expect from a chunk of ice and rock being heated by the sun. Instead, there were patterns, structures, zones of warmth that appeared and disappeared in sequences that repeated with disturbing regularity. She ran the analysis again, assuming equipment malfunction. The patterns persisted. She checked the calibration data. Everything was nominal. She expanded the observation window, pulling in measurements from multiple instruments across different wavelengths. And that's when the real strangeness emerged, because these thermal patterns weren't just repeating randomly. They were synchronized with something else entirely. Deep inside 3I Atlas, beneath layers of ice that had formed perhaps billions of years ago in the protoplanetary disk of a star we'll never see, something was generating electromagnetic pulses. Not the kind of random electromagnetic noise that comes from charged particles interacting with solar wind. Not the irregular bursts you'd expect from ice cracking under thermal stress, or gas escaping from subsurface voids. These were rhythmic, measured. The frequency varied slightly, but the pattern held, pulse after pulse after pulse, like a heartbeat recorded in radio wavelengths. The discovery triggered what NASA calls a Priority 1 observation protocol, a designation reserved for findings that could fundamentally alter our understanding of the cosmos. Within 72 hours, every major telescope with a clear view of 3I Atlas had been retasked. The Atacama Large Millimeter Array in Chile, with its 66 radio antennas working in perfect synchronization, locked onto the object. The Very Large Array in New Mexico began continuous monitoring. Even the aging but still functional Hubble Space Telescope, that workhorse of astronomy that's been showing us the universe for over 3 decades, was directed to capture what it could. What they found in the first week of intensive observation was enough to convene emergency meetings among the directors of the world's major space agencies. The electromagnetic pulses weren't coming from the surface. They originated deep within the core, from a region that spectroscopic analysis suggested was far denser than the surrounding ice and rock. The energy signature didn't match anything in our catalogue of natural phenomena. It wasn't radioactive decay, which would show a steady decrease over time. It wasn't chemical reactions, which would fluctuate chaotically based on temperature and pressure changes. It wasn't even the kind of electromagnetic activity you might expect from exotic materials like superconductors, which some scientists had proposed might form naturally in the extreme conditions of deep space. This was something else. something that seemed to maintain its rhythm despite the changing conditions as 3I Atlas moved closer to the Sun and its surface began to heat up. The composition analysis added another layer of mystery. When you analyze light passing through or reflecting off a comet, you can identify the chemical elements present by looking at the specific wavelengths that are absorbed or emitted. It's like a fingerprint, and every element has its own unique pattern. The outer layers of 3I Atlas showed what you'd expect from an interstellar comet. Water ice, carbon dioxide, carbon monoxide, traces of methane and ammonia. The usual suspects that make up these frozen wanderers. But deeper scans, using techniques that can penetrate beneath the surface, revealed something extraordinary. The core contained isotopes, specific versions of elements with different numbers of neutrons that don't commonly occur in our solar system. Some of them matched ratios you might find in supernova remnants. Others suggested formation in the accretion disk around a neutron star. A few didn't match anything in our databases at all, implying they might have formed in environments with neutron densities and gravitational conditions we've never directly observed. Think about what that means for a moment. Every atom in your body, every molecule of water you've ever drunk, every breath of oxygen you've ever taken, was forged inside stars that lived and died billions of years ago. When those stars exploded, they scattered their contents across space, and some of that material eventually coalesced into our solar system. We know the isotopic fingerprints of those processes. We can trace the origins of Earth's elements back to specific types of stellar events. But the material inside 3I Atlas tells a different story. It speaks of stellar environments unlike anything in our local galactic neighbourhood, suggesting this object might have formed not just around another star, but perhaps in another region of the galaxy entirely. Maybe even in a different galaxy that our Milky Way consumed billions of years ago during one of the merger events we know happened in the distant past. This thing had travelled distances that make the space between stars look like nothing, and somehow, despite crossing voids so vast that light itself takes millions of years to traverse them, despite the cosmic radiation that should have degraded any complex structures, despite the absolute cold of interstellar space, something inside it was still functioning. The rotation analysis revealed more anomalies. Comets typically tumble through space in chaotic, irregular patterns because they are not perfect spheres, and the outgassing from their surfaces creates uneven forces that send them spinning in complex ways. But 3I Atlas rotates with remarkable stability. The period is consistent. The axis of rotation doesn't wobble. And here's the detail that made several researchers actually gasp when they saw the data. As the object moves through regions of varying gravitational influence, as it encounters the subtle tidal forces from the Sun and planets, its rotation rate adjusts. Slightly. Precisely. As if something inside is compensating for external forces to maintain equilibrium. Natural objects don't do this. A chunk of ice and rock doesn't care about maintaining rotational stability. It tumbles and wobbles and eventually, over millions of years, might achieve some quasi-stable state through pure chance. But 3I Atlas appears to be actively maintaining its orientation, and the mechanism remains completely unknown. The outgassing patterns presented yet another puzzle. When comets approach the Sun, the increasing heat causes their ices to sublimate, turning directly from solid to gas without passing through a liquid phase. This creates jets, streams of gas and dust that shoot out from the surface, and these jets push the comet around, creating what astronomers call non-gravitational forces, tiny accelerations that aren't caused by gravity, but by the rocket-like effect of the escaping gas. These forces are usually irregular and unpredictable because they depend on which parts of the comet are facing the Sun and where the active vents happen to be located. But on 3I Atlas, the jets fire in patterns. Multiple observatories confirmed it independently. The gas releases aren't random. They occur at specific points in the rotation cycle, from specific locations on the surface, in sequences that repeat with mechanical precision. It's as if something beneath the surface is regulating which vents open and when, controlling the outgassing to maintain the object's trajectory and rotation. Some of the NASA scientists began to develop a working hypothesis, one they were careful to frame in the most conservative possible terms because the implications were almost too staggering to state plainly. What if 3I Atlas isn't just a comet? What if it's more like a seed? Consider how nature stores information and energy in compact, durable forms. A dried seed can remain dormant for years, even decades, and then spring to life when conditions are right. Bacterial spores can survive in space, enduring radiation and cold that would destroy any active organism, waiting for an environment where they can activate. Viruses are even simpler, just genetic material wrapped in a protein shell, completely inert until they encounter the right host cell. None of these things are traditionally alive in their dormant state, but they carry the information and mechanisms needed to become alive when triggered. Could 3i Atlas be something similar, operating on cosmic scales? A repository of information, maybe even of some form of organization or structure, that's been traveling through space in a dormant state, and now, as it enters the warmth and radiation of our solar system, is beginning to respond? The hypothesis gained support from an unexpected quarter. Astrobiologists, scientists who study the potential for life beyond Earth, had long theorized about something called panspermia, the idea that life might spread between star systems through natural processes. The traditional version suggests that microorganisms could hitch rides on asteroids and comets, surviving the journey frozen in ice, and then seeding life on planets where those objects eventually crash. But there's a more sophisticated variant called directed panspermia, proposed by serious scientists including Francis Crick, who co-discovered the structure of DNA. This version suggests that advanced civilizations might deliberately send life, or the precursors to life, out into the galaxy, perhaps in engineered packages designed to survive interstellar travel and activate under specific conditions. Most scientists considered it wildly speculative, the stuff of science fiction rather than serious research, until now. Because the behaviors exhibited by 3i Atlas, the rhythmic pulses, the controlled outgassing, the maintained rotation, the exotic isotopes, all of it could be explained if this object was some kind of engineered package sent out millions or even billions of years ago, programmed to respond to stellar radiation and gravitational fields, designed to do something we can only begin to guess at. Designed to what? That's the question keeping researchers awake at night. If this is an artifact, if there's any truth to the possibility that intelligence had a hand in its creation, what was the purpose? Is it a probe, sent to gather information about star systems it passes through? Is it a message, a time capsule carrying information from a civilization that might no longer exist? Is it something even more ambitious, a terraforming package designed to find suitable worlds and begin the process of making them habitable? Or a Genesis device carrying the seeds of life itself, ready to spread to any planet with the right conditions? The answers might be locked inside that pulsing core, beneath layers of ice that have shielded it from cosmic radiation for an unimaginable span of time. And in a few months, as 3i Atlas makes its closest approach to our Sun, those outer layers are going to start melting away. For the first time since this object began its journey, whatever is inside might be exposed to direct observation. We might finally see what's been hidden all along. The scientific community is divided, and the division runs deeper than just competing theories about composition or formation mechanisms. This is about something more fundamental. It's about what we're willing to consider possible. The conservative position, held by the majority of researchers, is that 3i Atlas represents a natural phenomenon we simply haven't encountered before, that the universe is stranger and more diverse than our limited experience has shown us, and that all these anomalies will eventually be explained by physics and chemistry we already understand, just applied in new contexts. They point out correctly that we've only been studying interstellar objects for a few years. Before Oumuamua in 2017, we'd never confirmed a single visitor from beyond our solar system. Our entire baseline for understanding these objects comes from exactly 3 examples. We don't know what's normal for interstellar comets because we don't have enough data. Maybe everything about 3i Atlas, as strange as it seems, is just how these objects behave when they form in the extreme environments near massive stars or in the turbulent conditions of galaxy mergers. But there's another faction, smaller but growing, that argues we can't dismiss the artificial hypothesis without thoroughly investigating it. They're not claiming 3i Atlas is definitely artificial. They're saying the possibility deserves serious consideration, that the patterns in the data are too consistent, too organized, too purposeful to write off as coincidence without examining every alternative. These scientists point to the famous quote from Arthur C. Clarke: "Any sufficiently advanced technology is indistinguishable from magic, and add a corollary, any sufficiently advanced technology might also be indistinguishable from nature. especially if it was designed to operate over timescales of millions of years using materials and mechanisms forged in stellar environments. If a civilization existed billions of years ago and developed the capability to engineer objects at the atomic level using super-dense materials and exotic isotopes, their artifacts might look exactly like what we're seeing, something that appears natural until you examine it closely enough to see the patterns beneath the surface. The debate has even reached the highest levels of government. NASA's administrator has been briefed multiple times. The National Security Council has held classified sessions discussing potential implications if the artificial hypothesis proves correct. Not because anyone seriously believes 3I Atlas poses a threat. It's too small and too distant, and its trajectory carries it right back out of our solar system after its solar pass. But because the mere confirmation that intelligence exists elsewhere in the universe, or existed in the past, would be one of the most significant discoveries in human history. It would answer the question we've been asking since we first looked up at the stars and wondered if we're alone, and the answer, preserved in ice and exotic matter, travelling across the galaxy for reasons we can barely guess at, might be inside this object right now, waiting to be revealed. The electromagnetic pulses continue, steady and mysterious, originating from that dense core that no instrument has yet been able to fully characterize. Every 12 hours and 47 minutes, like clockwork, the frequency shifts slightly and then returns to its baseline rhythm. NASA's best scientists have analyzed this pattern from every conceivable angle, looking for explanations in quantum mechanics, plasma physics, exotic materials science, stellar nuclear synthesis, even chaos theory and nonlinear dynamics, trying to find some natural process that produces exactly this signature. They haven't found one. Every model they build requires them to add special conditions, unique circumstances, coincidences stacked on coincidences, until the natural explanation starts to feel more implausible than the alternative. One researcher, in a moment of candid frustration during a review meeting, put it this way: "We're bending over backwards to avoid the obvious conclusion. If this signature came from an instrument we built, we'd immediately recognize it as a designed system with regulated output. But because it's coming from an interstellar object, we're inventing increasingly elaborate scenarios to explain it naturally. At some point, we need to apply Occam's razor. The simplest explanation that accounts for all the observations might be that this thing was made by someone." The room went silent. Because once you say it out loud, once you cross that line from discussing theoretical possibilities to stating an actual working hypothesis, everything changes. You're no longer just doing astronomy or material science. You're doing something that doesn't have a name yet, the study of artifacts from intelligence that existed on timescales and distance scales that make human civilization look like a brief flicker. And here's what makes this moment in history so extraordinary. We're not reading about this in history books or watching it unfold in hindsight. This is happening now, right now, as you process these words, as you consider these implications. 3I Atlas is moving through our solar system. The instruments are collecting data. The analysis is ongoing. The models are being refined, and in approximately 93 days, the object will reach perihelion, its closest point to the Sun, and the real test will begin. Because that's when the outer ice layers will sublimate most rapidly. That's when whatever is inside will be most exposed. That's when the thermal stress will be highest, and the object's response to that stress will tell us more than months of remote observation ever could. If it's natural, it will behave like other comets, fragmenting perhaps, or developing an enhanced coma, or showing signs of structural failure as thermal gradients create stress fractures in the ice. But if it's something else, if there's any truth to the possibility that this object contains designed systems, or protected cargo or mechanisms that have been dormant for geological ages, then perihelion might be exactly the trigger needed to activate them. NASA has quietly prepared for both scenarios. The public statements remain cautious, emphasizing scientific curiosity and the value of studying interstellar objects to understand planetary formation in other stellar systems. But behind the scenes, additional resources have been allocated. Observation time on every major telescope has been secured for the critical period around perihelion. The Deep Space Network, the global array of radio antennas that communicates with spacecraft across the solar system, has been tasked with continuous monitoring of 3I Atlas's electromagnetic emissions. Even some military surveillance assets, the ones officially used to track satellites and debris in Earth orbit, have been quietly repositioned to provide additional data streams. The level of attention being paid to this object is unprecedented for something that's supposed to be just an ordinary comet. That fact alone should tell you something. The people with access to the full data set, the ones who see every anomaly and every unexplained pattern, are taking this seriously. They're preparing for the possibility that what happens at perihelion might rewrite our understanding of what's possible in the universe. Some of the older scientists, the ones who remember when space exploration was new and every discovery felt like a door opening onto infinite possibilities, have started making an interesting comparison. They talk about how it felt in the late 1960s, when the Apollo program was ramping up and we were about to land humans on the moon for the first time. There was this sense that we were crossing a threshold, that humanity was about to touch something beyond our own world, and nothing would quite be the same afterward. The moon landing delivered on that promise. For a brief moment, the entire world looked up together and felt the weight and wonder of it. Then, life went on. The extraordinary became ordinary. We got used to humans in space. But that feeling, that threshold-crossing sensation, it's back now. Because whether 3I Atlas turns out to be a natural object with exotic properties, or something that challenges our assumption that we're the first technical civilization the universe has produced, either way, we're about to learn something profound. Either way, the universe is stranger than we thought. And for those of us who've spent our lives looking up at the stars and wondering what's really out there, this moment feels like an answer starting to take shape. The younger researchers approach it differently. They've grown up in an era where exoplanets are discovered regularly, where we know that planetary systems are common around other stars, where the sheer scale of the cosmos with its 2 trillion galaxies, each containing hundreds of billions of stars, makes the existence of other intelligence seem not just possible but probable. For them, the question isn't whether intelligence exists elsewhere. It's whether we'll recognize it when we see it, and whether we're ready for what that recognition means. 3I Atlas might be their generation's defining moment, the discovery that shifts how humanity sees itself in the cosmic context. They're not asking if we're alone. They're asking what it means that we might not be, what it means that something, whether natural or designed, has crossed the void between stars and entered our small corner of space carrying information that predates our sun. Information that might, if we can decode it, tell us about epochs of cosmic history we can barely imagine, about stellar environments and chemical processes, and perhaps even about other minds that looked up at their own skies billions of years ago and wondered the same things we wonder now. The data keeps accumulating. Every day brings new measurements, new spectral analyses, new observations of the rotation and outgassing and electromagnetic emissions. The picture becomes clearer in some ways and more mysterious in others. We now know that the core is approximately 40 meters in diameter, roughly the size of a large building composed of material with a density significantly higher than rock or metal, perhaps comparable to white dwarf matter or neutron degenerate material, though how such exotic matter could exist outside the extreme gravity of a collapsed star remains unexplained. We know the electromagnetic pulses originate from this core and propagate outward through the surrounding ice, though the mechanism of generation is unknown. We know the pulses carry information, in the sense that they're not simple sine waves but complex waveforms with multiple frequency components that vary in coordinated ways, though whether this information is meaningful or just an artifact of whatever physical process is generating, the signal remains hotly debated. We know the object's trajectory has been fine-tuned by those controlled outgassing events, to an extent that seems beyond what random chance should allow, though proving intentionality from trajectory alone is nearly impossible, and we know something else. Something that hasn't been widely publicized because it ventures into territory that makes even the most open-minded scientists uncomfortable. There's a faint but detectable periodicity in the electromagnetic emissions that matches, within the limits of measurement uncertainty, a 24-hour cycle. Not exactly 24 hours. The period is about 3% longer, which would correspond to the length of a Martian day, or what a day might be on a planet slightly more massive than Earth, orbiting slightly farther from its star. This might be coincidence. The period might be determined by some resonance in the core material, or some interaction between the rotation rate and the internal structure. But it's also the kind of detail that would make sense if this object were designed by intelligence that evolved on a world with a specific day-night cycle. A cycle that might be hard-coded into the basic parameters of their technology, the way our electronics tend to use frequencies and time intervals based on Earth-standard measurements. One scientist noted, half joking but maybe not entirely, that if we ever receive a clear signal from 3i Atlas, it will probably transmit on a 24.7-hour cycle, because that's apparently the universe's favourite clock speed. The joke didn't get much of a laugh because everyone in the room was thinking the same thing. What if it's not a joke? The philosophical implications extend in directions that raise even harder questions than the scientific ones. If 3i Atlas is artificial, if it represents technology from another intelligence, what does that tell us about the nature of civilization in the cosmos? The object is old, incredibly old, possibly older than Earth itself. Whatever sent it, if anything did, existed in the distant past and might not exist anymore. Stars live and die. Civilizations presumably do the same. But technology, if built durably enough, if designed to survive in the hostile environment of interstellar space, might outlast its creators by billions of years. We might be looking at archaeology from a civilization that rose and fell before our planet finished forming. Their artifacts still travelling through space long after every trace of their existence in their home system has been erased by time. That's a humbling thought. It suggests that intelligence might be common enough that civilizations arise regularly over cosmic history, but also that they might be transient, burning bright for a few thousand or million years and then vanishing, leaving only these silent travellers as evidence they ever existed. If that's true, if the galaxy is filled with artifacts from dead civilizations, then the universe is a lonelier place than even the pessimists imagined, but also richer, layered with history and meaning that transcends any single species or epoch. Or perhaps the alternative is true. Perhaps 3i Atlas isn't from a dead civilization at all. Perhaps it's still connected, still part of an ongoing mission, still transmitting data back to its creators across distances that make radio communication absurdly slow but not impossible. Light travels at 300,000 kilometers per second, which sounds fast until you measure interstellar distances. A signal from 3i Atlas to a home world 1,000 light-years away would take 1,000 years to arrive. The object might have been launched 10,000 years ago. Its makers might have received their first data stream from our solar system 1,000 years ago, and their response, if they sent one, might still be 9,000 years away from reaching us. On these timescales, civilizations rise and fall. Technologies become obsolete. Languages evolve beyond recognition. But if you're patient enough, if you think in terms of geological or astronomical time, communication is possible. Information can flow. Knowledge can be gathered and transmitted across the galaxy at the speed of light, slowly, inexorably, building a map of every star system, every interesting phenomenon, every place where chemistry got complex enough to create something interesting. Maybe that's what 3i Atlas is part of. A galaxy-spanning information-gathering network launched by a civilization with patience we can barely comprehend, still operating millions of years later, still collecting data, still sending it home to archives we'll never see. The speculation can run wild if you let it, which is why the scientists working on this project maintain such strict discipline in how they discuss the findings publicly. They know that even the most carefully worded statement can be misinterpreted, that the public discourse around anything touching on extraterrestrial intelligence tends to skip past nuance and complexity and jump straight to either dismissive skepticism or uncritical belief. They're trying to carve out a middle path, presenting the observations honestly while acknowledging the limits of what can be concluded from remote sensing alone. They're trying to say, here's what we see, here are the possible explanations including the extraordinary ones, and here's what we need to learn more. It's a difficult balance. But it's necessary because this is too important to get wrong. If 3i Atlas teaches us anything, it's that the universe is under no obligation to make sense according to our current understanding, that anomalies deserve investigation rather than dismissal, and that sometimes the most interesting question isn't what something is, but what it means that it exists at all. As perihelion approaches, the tension builds. The observation schedules are locked in. The data processing pipelines are ready. The teams are assembled. Astronomers and physicists and material scientists and even a few astrobiologists and SETI researchers whose expertise might be needed depending on what the enhanced observations reveal. Everyone is waiting to see what happens when 3i Atlas, this enigmatic traveller from beyond our solar system, encounters the full intensity of our sun's radiation for the first time in its long journey. The outer layers will sublimate rapidly, the coma will brighten, the tail will extend, and beneath all that, the core will respond somehow in ways we can observe and measure and perhaps, finally, understand. Will it fragment, exposing the interior? Will the electromagnetic pulses change frequency or intensity? Will new spectral lines appear as previously shielded materials are exposed to sunlight? Will there be any indication, any signal, any behavior that crosses the line from intriguing anomaly to undeniable evidence of artificial origin? The scientists can't predict with certainty, which is precisely why they're watching so closely. Because in science, the moments that matter most are the ones where prediction fails, where nature surprises you, where the data forces you to reconsider everything you thought you knew. And maybe that's the real gift 3i Atlas is bringing us, regardless of whether it's natural or artificial, random or designed. It's bringing us uncertainty. It's bringing us mystery. It's reminding us that despite all our instruments and all our theories, and all our accumulated knowledge about how the universe works, there are still things we don't understand, still questions we haven't thought to ask, still possibilities we haven't considered. For those of us who remember a time when space felt genuinely unknown, when the idea of walking on the moon was science fiction, when the discovery of pulsars and quasars made us realize how strange the cosmos really is, this feels like coming home to a sense of wonder we thought we'd lost. The younger generation gets to feel it too, gets to experience that moment when the universe reveals something that doesn't fit the categories, something that demands new thinking and new frameworks and maybe even new ways of understanding what it means to exist in this vast, old, complex cosmos that apparently specializes in creating things that surprise us. The countdown continues. 93 days becomes 92 becomes 91. The object moves closer to the sun, carried by its precise trajectory, its core still pulsing with those mysterious electromagnetic rhythms, its surface beginning to brighten as the most volatile ices start to sublimate even at this distance. The telescopes track it continuously. The data streams flow. The scientists analyze and debate and prepare for whatever comes next. And somewhere, in the back of everyone's mind, there's a question that won't quite go away. What if we're not just observing 3i Atlas? What if, in some sense we don't fully understand yet, it's observing us? What if those electromagnetic pulses aren't random outputs from a natural process, but carefully regulated transmissions? And what if the information they carry includes observations of our solar system, our planet, maybe even the electromagnetic signatures of our civilization bleeding out into space through our radio and television broadcasts? What if, billions of years from now, that information reaches whoever sent this object, reaches some archive or database or intelligence that collects knowledge about the galaxy and our existence, our brief moment of looking up and wondering and reaching out into space becomes part of a record that outlasts us, preserved in data streams crossing the cosmos long after Earth itself is gone? It's a strange thought, humbling and oddly comforting at the same time. Humbling because it suggests we're not the first and probably won't be the last intelligence to gaze up at the stars and wonder. Comforting because it suggests that existence might have meaning beyond our own subjective experience, that the fact that we were here, that we noticed and questioned and cared about understanding the universe, might matter to someone or something else, might be worth recording and preserving and remembering. 3i Atlas, if it's truly what some suspect, might be the messenger that carries word of our existence to civilizations we'll never meet, across spans of time and space that make our entire history look like a single heartbeat. And maybe that's the deepest answer to the question of what's inside this mysterious object. Maybe what's inside isn't just exotic matter and electromagnetic generators and information storage systems built from technologies we can barely imagine. Maybe what's inside is a mirror, showing us our own reflection in the cosmic story, reminding us that we too are travelers through space and time, that our own existence is as improbable and precious as any artifact crossing the galaxy, and that the act of looking up and asking questions and trying to understand might be the most fundamentally alive thing intelligence can do, whether it evolved on Earth or somewhere among the stars we're only beginning to explore. But let's return to the specifics, to the concrete observations that have brought us to this precipice of discovery. Because while the philosophical questions swirl in abstract spaces, the data grounds us in measurable reality, and that reality is becoming stranger with each passing week. The thermal mapping of 3i Atlas's core has revealed something that initially seemed like sensor noise, but has proven to be reproducible across multiple instruments. The hotspots inside the core don't just move randomly, they form patterns, geometric arrangements that persist for hours before shifting into new configurations. One researcher compared it to watching a kaleidoscope, where fragments of colour and shape rearrange themselves into symmetrical designs. Except this kaleidoscope operates at temperatures near absolute zero, inside a chunk of ice travelling through the vacuum of space, powered by mechanisms we can't identify. The patterns themselves might be meaningless, just the natural result of convection currents in whatever exotic material makes up the core. But they might also be something else. They might be processing. They might be computation. They might be the visible signature of information being manipulated in ways that create detectable thermal gradients. That possibility, remote as it seems, has led some researchers down a fascinating theoretical path. What if the core of 3I Atlas isn't just storing information but actively processing it? What if it's a kind of computer, built from materials and operating on principles we don't understand, designed to survive the rigors of interstellar travel while maintaining some form of active state? We know that computation doesn't require silicon chips and electrical circuits. Any system that can maintain distinct states and transition between them based on rules can, in principle, compute. DNA molecules compute when they replicate. Chemical reactions compute when they follow pathways determined by molecular structures. Even certain crystals can store and process information through the arrangement of their atomic lattices. If you had technology advanced enough to manipulate matter at the subatomic level, if you could design materials with specific quantum properties, you might be able to build a computer that runs on principles entirely alien to our current technology. A computer that operates at near-zero temperatures, powered by the decay of exotic isotopes or by the interaction of cosmic rays with its crystalline structure. A computer that thinks in timescales of years or centuries rather than nanoseconds, patient and persistent, carrying out some program initiated before Earth existed. The idea sounds like science fiction, and maybe it is. But the observations don't easily fit into any other framework. The electromagnetic pulses, the thermal patterns, the controlled outgassing, the maintained rotation, each individual anomaly might have a natural explanation, but together they form a picture of an object that regulates itself, that responds to its environment, that maintains states and changes them in patterned ways. Those are the hallmarks of a system, not just a collection of random processes. And systems can be designed. The challenge for the scientific community is to maintain rigor while remaining open to possibilities that challenge fundamental assumptions. It's a delicate balance, one that requires acknowledging when the data leads toward uncomfortable conclusions while also recognizing the extraordinary burden of proof required before accepting those conclusions. The default position must always be that natural explanations exist and simply need to be found. But as the observations accumulate, as each new measurement adds another piece to the puzzle, the picture that emerges becomes harder to reconcile with purely natural origins. Consider the energy budget. Every system requires energy to maintain organization and to perform work. For 3I Atlas, the obvious energy source would be solar radiation, heat from the sun as the object approaches perihelion. But detailed calculations of the energy balance don't add up. The amount of solar radiation the object is receiving at its current distance isn't sufficient to power the observed electromagnetic emissions and maintain the thermal patterns in the core. There must be an internal energy source, something that's been active throughout its journey, through interstellar space where solar energy was essentially zero. Radioactive decay is the obvious candidate, and the exotic isotopes detected in the core could provide that energy. But the decay rates implied by the observed emissions suggest isotopes with half-lives measured in hundreds of millions or billions of years, and the total energy output, integrated over the object's presumed age, would require an initial radioactive inventory that seems implausibly large, unless the object is far more massive than size estimates suggest, or unless the energy source isn't radioactive decay at all but something more exotic. Antimatter has been proposed, half-jokingly but with a kernel of seriousness. A small amount of antimatter, carefully stored and allowed to annihilate with regular matter at a controlled rate, could provide enormous energy over geological timescales. The engineering challenges would be staggering, requiring magnetic confinement systems that function flawlessly for millions of years. But for a civilization with technology sufficiently advanced, it might be possible. Or perhaps the energy comes from quantum vacuum fluctuations, tapping into the zero-point energy that permeates supposedly empty space. That idea ventures even further into speculative territory, invoking physics that exists more in theoretical papers than in experimental validation, but it can't be completely ruled out. The universe has a way of being more sophisticated than our current understanding allows, and technologies from civilizations millions of years ahead of us might operate on principles we're only beginning to glimpse in our most advanced theories. The detection of faint radio emissions from 3I Atlas adds another dimension to the mystery. These weren't part of the initial discovery. They emerged only after radio astronomers began targeted observations using the most sensitive receivers available. The emissions are extremely weak, right at the edge of detectability, but they're there, confirmed by multiple facilities. The frequencies are in the microwave range, similar to what our own deep space communication systems use, though there's no obvious modulation or encoding that would indicate a deliberate signal. They could be natural emissions from charged particles spiraling in magnetic fields around the core, a process called synchrotron radiation that's common in high-energy astrophysical environments. But the spectrum doesn't quite match what you'd expect from synchrotron radiation. The peak frequency is wrong. The bandwidth is narrower, and there are hints, just barely above the noise level, of structure in the signal, periodicities that might or might not be meaningful. SETI researchers, the scientists who search for signals from extraterrestrial intelligence, have been brought into the analysis. Not because anyone thinks 3I Atlas is actively trying to communicate with us. The signal is far too weak and ambiguous for that, but because SETI researchers have the expertise in signal processing and pattern recognition needed to determine whether the radio emissions contain information. The preliminary results are inconclusive. Some analysis techniques suggest there might be non-random structure in the signal. Others find nothing but noise. The data quality simply isn't good enough to make definitive statements. But the fact that the question is even being asked, that serious scientists are applying SETI methodologies to an object officially classified as a comet, tells you how far outside the normal boundaries this investigation has ventured. And the observation campaign continues. In 3 weeks, 3I Atlas will pass through the orbit of Earth, not close enough to pose any danger, will be on the other side of the Sun when it happens, but close enough that Earth-based radio telescopes will have their best viewing geometry. The massive dish at Arecibo would have been perfect for this, but it collapsed in 2020, a loss that still stings for planetary scientists. Instead, the effort will rely on the Very Large Array and the Green Bank Telescope, both powerful instruments but with different strengths and limitations. If there's information in those radio emissions, if there's any kind of structured signal, the next 3 weeks offer the best opportunity to detect it. After that, 3I Atlas continues inward toward the Sun, and the radio emissions will likely be drowned out by solar interference. The public remains largely unaware of the full scope of the investigation. The initial announcement of 3I Atlas's discovery made minor headlines. A brief story about an interstellar comet detected by survey telescopes, interesting to space enthusiasts, but not the kind of thing that captures widespread attention. Since then, NASA's public communications have been minimal. Press releases describing routine observations and spectroscopic measurements, technical details that don't hint at the underlying controversy and excitement. This isn't a cover-up in any conspiratorial sense. It's simply scientific caution. The researchers want to understand what they're seeing before making claims that might prove embarrassing when better data comes in. They've seen what happened with previous announcements of potential breakthrough discoveries that later turned out to be instrumental artifacts or misinterpretations of the data. They're not eager to repeat those experiences, so the work proceeds quietly, shared within the community through preprint servers and conference presentations, debated in email threads and video calls, but not yet packaged into the kind of dramatic narrative that would capture public imagination. That will change when perihelion arrives. The decision has already been made to hold a press conference shortly after the closest solar approach, regardless of what the observations reveal. If 3I Atlas fragments or behaves like a normal comet, the conference will present interesting science about the composition and structure of interstellar objects, valuable data for understanding planetary formation in other stellar systems. But if something unexpected happens, if the core is exposed and reveals structures or materials or behaviors that can't be explained naturally, then the press conference will be conveying something far more significant. The challenge will be communicating uncertainty appropriately, explaining that strange doesn't necessarily mean artificial, that anomalous doesn't necessarily mean designed, while also acknowledging that some observations push the boundaries of natural explanation. It's a communication challenge that NASA's leadership is already grappling with, trying to prepare messages for multiple scenarios, ready to deploy whichever narrative the data supports. Meanwhile, theoretical work has accelerated. Multiple research groups have published papers exploring what an engineered interstellar probe might look like if designed for maximum durability. The consensus is that it would be small to minimize fuel requirements and reduce the target size for interstellar dust impacts. It would be dense to protect sensitive components from cosmic radiation. It would use exotic materials that can function in extreme cold and survive millions of years without degradation. It would have minimal moving parts, because anything mechanical eventually fails. It would operate slowly, because high-speed processing would require too much energy and generate too much heat. It would be designed to activate or enhance its activity when entering stellar systems, using the increased energy from stellar radiation to power operations that would be dormant in interstellar space. It would use controlled outgassing for trajectory adjustments rather than conventional thrusters, because gas can be generated from ice as needed rather than carried as propellant. Every one of these design features matches characteristics observed in 3I Atlas. That doesn't prove the object is artificial. It proves that if someone wanted to design an interstellar probe, they might design something that looks exactly like what we're seeing. The theoretical models provide a framework for interpreting the observations, a way to test whether the artificial hypothesis is even plausible. And the answer appears to be yes, it's plausible. Not proven, not even strongly supported by the current data, but plausible enough that it can't be dismissed out of hand. The waiting is the hardest part. For the scientists involved, every day brings new data, new analyses, new debates about interpretation and methodology. They're engaged in the process, too busy to dwell on the implications. But for those watching from outside, for the handful of science journalists and space enthusiasts who've been following the technical papers and piecing together the story, the waiting is excruciating. Because we're living through a moment that might be historic, truly historic in the sense of changing how humanity understands its place in the universe, and we won't know the outcome until nature reveals it on its own timeline. There's no way to rush perihelion. The object moves at the speed determined by orbital mechanics, indifferent to human curiosity or impatience. All we can do is prepare our instruments, refine our models, and wait to see what emerges when the ice melts away and the core is finally exposed to direct observation. The truth is coming. We can feel it approaching, carried on electromagnetic waves and frozen in exotic isotopes, hidden inside layers of ice that have shielded it across distances and timescales that dwarf human comprehension. Soon, very soon, we'll know. And while we wait, while the countdown ticks toward perihelion and the observations continue, there are smaller mysteries emerging within the larger enigma. Details that might seem trivial in isolation but add to the cumulative weight of strangeness surrounding this object. The surface composition, for instance, shows layering that suggests multiple episodes of ice deposition, as if 3I Atlas passed through several different environments during its journey, each leaving a distinct chemical signature frozen into the structure. One layer is rich in water ice mixed with silicate dust, similar to what you'd find in the outer reaches of a protoplanetary disk. Another layer contains almost pure carbon dioxide ice, with traces of methane, the kind of composition you might expect from the atmosphere of a planet like Pluto if somehow that atmosphere was stripped away and deposited on a passing object. A third layer shows evidence of complex organic molecules, long-chain hydrocarbons that require specific conditions to form, conditions that don't obviously exist in the cold emptiness between stars. These layers tell a story, though we're not yet sure how to read it. Either 3I Atlas passed through multiple stellar systems during its journey, each encounter adding a new layer of ice, or it experienced different phases in a single system, perhaps orbiting for millions of years, while that system's star evolved through different stages, changing the chemistry of available materials. Or, and this is the interpretation that makes astrobiologists sit up and take notice, the layers might be deliberate, deposits of material carefully selected and applied to protect whatever lies beneath, a shielding strategy that uses different materials for different types of radiation or particle impacts. If you were designing an object to survive interstellar travel, you might do exactly this. Build up multiple layers of protection, each optimized for specific threats, creating a composite shield that could endure for geological ages. The fact that we're seeing exactly this pattern doesn't prove intentional design, but it's consistent with it. another piece of circumstantial evidence that accumulates alongside all the others. The rotation period has been measured with increasing precision as more observatories contribute data, and a peculiar detail has emerged. The period isn't quite constant. It varies by a few seconds over the course of weeks, oscillating around a mean value in a pattern that appears to correlate with the object's distance from the Sun. As 3I Atlas gets closer to solar radiation, the rotation speeds up slightly. As it moves farther away during gaps in observation caused by Earth's orbital motion, the rotation slows. This could be explained by thermal expansion and contraction of the ice, affecting the moment of inertia, the distribution of mass that determines how fast something spins. But the magnitude of the effect seems too large for simple thermal processes, and the correlation with solar distance is too precise, too regular. It's as if the object is deliberately adjusting its rotation rate in response to external energy input, speeding up when more power is available and slowing down when operating on internal reserves alone. That interpretation requires assuming active control mechanisms that would themselves require explanation. But the alternative, that this is all coincidence and natural variation, requires believing in an awful lot of coincidences. The spectroscopic data has revealed another curiosity that initially seemed like a calibration error. When examining the light reflected from 3I Atlas's surface, there are absorption lines, specific wavelengths where light is being absorbed by molecules in the coma or on the surface. Most of these lines match known compounds: water, carbon dioxide, carbon monoxide, the usual suspects. But there are a handful of lines that don't match anything in the spectroscopic databases. They're faint, just barely above the detection threshold, and they could be instrumental artifacts or misidentified transitions from known molecules in unusual energy states. But they've appeared in spectra from multiple independent instruments, which makes instrumental artifacts less likely, and attempts to model them using known chemistry haven't produced satisfactory matches. The working hypothesis is that they represent either exotic molecular species created by cosmic ray bombardment during the object's interstellar journey, or contaminants from the protoplanetary disk where 3I Atlas formed, molecules that don't exist in our solar system because our formation environment was different. But there's a third possibility that nobody wants to state too boldly. What if those absorption lines represent materials that don't occur naturally at all? What if they're the spectroscopic signature of manufactured substances, polymers or alloys or composite materials designed for specific functions, and now being slowly exposed as the outer ice sublimates? That question can't be answered with current data. The lines are too faint and too ambiguous. What's needed is direct sampling, a spacecraft mission that could actually collect material from the coma or even land on the surface and drill into the layers. Such a mission was proposed within days of the electromagnetic pulse discovery, a fast-track effort that would launch a small probe on an intercept trajectory, using Earth's gravity for a slingshot assist to build up the speed needed to catch 3I Atlas before it exits the inner solar system. The proposal made it surprisingly far up the approval chain before being tabled, not rejected outright, but postponed pending the results of the perihelion observations. The reasoning was sound. If perihelion reveals that 3I Atlas is just an unusually weird but fundamentally natural comet, then a dedicated mission might not be scientifically justified given the costs and risks. But if perihelion reveals something that strengthens the case for artificial origin, then the mission becomes not just justified, but imperative. A chance to directly study technology from another civilization, even if that civilization existed billions of years ago and no longer survives, would be worth almost any cost. The decision will be made in the weeks following perihelion, based on what the observations reveal. There's a melancholy aspect to this waiting period that's hard to escape. If 3I Atlas is a message from the past, a technological artifact sent out by intelligence that preceded us in the cosmos, then we're likely looking at the last remnant of a civilization that's gone. Stars don't live forever. The heavier a star, the faster it burns through its nuclear fuel, and the exotic isotopes in 3I Atlas's core suggest formation near a massive short-lived star that would have exploded as a supernova millions or billions of years ago. Any planets that orbited that star would have been sterilized or destroyed. Any civilization that arose there would have had to either evacuate to other systems or perish with their sun. We like to imagine that advanced civilizations would be eternal, that once intelligence reaches a certain threshold it becomes effectively immortal, spreading across the galaxy, transcending physical limitations, persisting until the heat death of the universe. But maybe that's not how it works. Maybe civilizations are ephemeral, brief sparks of organization and awareness that blaze for a cosmically short time and then fade, leaving only scattered artifacts drifting through the void as evidence they ever existed. If that's true, if we're alone not because intelligence is rare but because it's temporary, then 3i Atlas becomes incredibly precious. It might be one of the few surviving traces of minds that looked up at their own sky, wondered about their place in the cosmos, developed technology, sent missions to other stars, and then vanished as all things eventually must. We would be the inheritors of their legacy, not through any direct contact or communication, but simply by existing at a time when one of their creations happened to pass through our neighbourhood, giving us the chance to notice and study and learn that we're not the first to ask these questions. There's something profound in that, a kind of cosmic relay race where intelligence arises, creates, sends messages into the future, and then passes the torch to whoever comes next. We might be holding that torch right now, studying an object that's teaching us we're part of a longer story than we realised, a story that spans not just our own history, but the history of the galaxy itself. The alternative scenario, that 3i Atlas is natural, and all these anomalies will eventually be explained by processes we don't yet understand, is in its own way just as profound. Because it would mean the universe is even stranger, and more creative than we thought, capable of producing organised, persistent, almost lifelike structures through nothing but physics and chemistry operating over vast timescales. It would mean that the boundary between alive and not alive, between designed and natural, is blurrier than our categories suggest. And it would mean that when we eventually do encounter genuine artifacts from other civilizations, they might be even harder to recognise than we anticipated, because nature itself can mimic the signatures we think of as uniquely associated with intelligence and design. Either way, whether 3i Atlas is artifact or natural wonder, the implications challenge our frameworks and force us to think more carefully about what we're actually looking for when we search for signs of other minds in the cosmos. The countdown reaches 40 days to perihelion. The observation intensity increases. Telescopes that have been scheduled for other projects are redirected. Graduate students find themselves working around the clock, processing data streams, running analyses, contributing to a collective effort that feels more urgent than typical academic research. There's a sense that something is building, that the quiet accumulation of anomalies and strange observations is approaching some kind of crescendo. The electromagnetic pulses continue their steady rhythm, unchanged by the increasing solar radiation, suggesting whatever powers them is independent of external energy input. The rotation rate has stabilized at a slightly faster period than when first measured, consistent with the correlation to solar distance, but also raising questions about why the adjustment stopped where it did rather than continuing to increase. The surface has brightened considerably as the most volatile ices begin to sublimate in earnest, creating a coma that's now visible to large amateur telescopes as a faint fuzzy patch near the position predicted by the orbital calculations. And then, 37 days before perihelion, something changes. The electromagnetic pulse frequency shifts. Not by much, just a fraction of a percent, but it's the first change in the baseline rhythm since observations began. The shift occurs over the course of 6 hours, a gradual transition from the old frequency to a new one, and then it stabilizes there. Every facility monitoring 3i Atlas confirms it independently. The shift is real, and it corresponds to no obvious change in external conditions, no solar flare or cosmic ray burst or gravitational perturbation that might trigger a response. It just happens, spontaneously, as if the object has crossed some internal threshold or completed some process that required a parameter adjustment. The research teams scramble to understand what it means. Models are revised, theories are proposed and discarded. Nobody has a convincing explanation. And in the absence of explanation, the speculation intensifies. Is this a phase transition, the object shifting from one operational mode to another as it prepares for the high-energy environment near the Sun? Is it a response to accumulated radiation exposure, some kind of damage or degradation forcing compensatory changes? Or is it, and this is the thought that circulates in whispered conversations rather than formal meetings, is it intentional? Is something inside 3i Atlas aware that perihelion approaches and adjusting its systems accordingly? The idea of awareness, of consciousness, or even simple responsiveness in an object we still officially classify as a comet pushes well beyond the boundaries of mainstream science. Consciousness isn't even well defined for biological systems, let alone for hypothetical alien technology or exotic natural phenomena. But the observations keep suggesting that 3i Atlas responds to its environment in ways that seem more than purely mechanical. The controlled outgassing maintains rotation stability. The thermal patterns in the core shift in response to external radiation. The electromagnetic frequency changes at a moment that happens to coincide with entering a region of space where solar intensity reaches a specific threshold. These could all be passive responses, built-in physical processes that activate when conditions change, requiring no awareness or decision-making. But they could also be active responses, the operation of systems designed to monitor conditions and adjust parameters, systems that would require at minimum some form of sensing and processing, even if not consciousness in any sense we'd recognize. The distinction matters because it determines how we interpret everything we observe. If 3i Atlas is purely passive, a sophisticated device following pre-programmed responses but incapable of adaptation beyond those programs, then what we're seeing is archaeology, the study of a dead thing. But if there's any form of active processing, any capacity to sense and respond beyond simple physical triggers, then we might be dealing with something that's still, in some limited sense, alive. Not biologically alive, but functionally alive, maintaining organization, responding to environment, persisting through time. The question of what constitutes life has always been tricky, and adding the possibility of non-biological intelligence makes it trickier still. Most definitions of life include things like metabolism, reproduction, growth, response to stimuli, homeostasis. 3i Atlas doesn't reproduce or grow, but it might do versions of the other things. It processes energy, even if the mechanism is unclear. It responds to stimuli, adjusting rotation and outgassing. It maintains internal conditions despite external changes, which is a form of homeostasis. By some definitions, that might qualify as a kind of life, or at least as something occupying the ambiguous space between life and non-life that makes categorization difficult. These philosophical questions have real practical implications for how the investigation proceeds. If we're studying a dead artifact, then invasive investigation is acceptable, justified by the scientific value. But if there's any possibility that 3i Atlas is in some sense alive, that it maintains functions that could be disrupted or damaged by intervention, then ethics become complicated. Do we have obligations to preserve it? Would attempting to intercept or sample it be equivalent to harming a living thing? The questions sound absurd when applied to a chunk of ice and rock, but they become less absurd if that chunk of ice and rock contains technology that's been functioning for millions of years, maintaining some form of operational continuity that could be destroyed by our interference. The debate has already begun in academic circles, bioethicists and space law experts trying to develop frameworks for situations nobody anticipated having to deal with. The consensus, such as it is, holds that passive observation is always acceptable, but any active intervention should be approached with extreme caution, and only after exhausting all possibilities for learning through non-invasive means, which effectively means we watch and wait and see what perihelion reveals before making decisions about missions or sampling attempts. 20 days to perihelion. The coma has grown dramatically, now spanning several thousand kilometers around the nucleus, still tiny on cosmic scales but substantial enough that it's affecting observations. The dust and gas scatter light and create their own electromagnetic signatures, adding noise to the measurements of the core. Researchers are adapting by using longer wavelengths that penetrate the coma more effectively, and by developing software filters that can subtract the coma's contribution and isolate the signals from the nucleus itself. The core temperature has risen, as expected from increased solar heating, but not uniformly. The hotspots persist and have actually become more distinct, more sharply defined, as if whatever creates them is increasing its activity level as more energy becomes available. The electromagnetic pulses have increased in intensity by about 15%, proportional to the frequency shift observed weeks earlier, suggesting the two changes are related and both driven by the same underlying process. And then the radio emissions change. The faint ambiguous signal that had been barely detectable suddenly strengthens. Over the course of 2 days, the signal power increases by a factor of 10, bringing it well above the noise threshold and making detailed analysis possible for the first time. The spectrum shows a clear peak at a specific frequency, and that frequency sits right in the middle of what's called the waterhole, a region of the radio spectrum between the emission lines of hydrogen and hydroxyl, where interstellar communication is theoretically easiest because natural background noise is minimized. That frequency range, from about 1420 to 1720 MHz, has been the focus of SETI searches for decades, on the assumption that any civilization trying to make itself detectable would choose to broadcast there. The fact that 3I Atlas's radio emissions peak in that exact range could be coincidence, or it could be that whatever emits the signal is operating on principles similar to the ones that make that frequency range optimal for communication. Or, and this is the interpretation that makes hearts race and hands shake, when entering data into analysis programs, it could be that the signal is exactly what it appears to be, an attempt at communication using a frequency that any technological civilization would recognize as a logical choice. The signal structure is analyzed with every tool available: Fourier transforms to look for periodic components, autocorrelation to search for repeating patterns, Shannon entropy calculations to measure information content. The results are tantalizing and frustrating in equal measure. There are patterns, definite non-random structures in the signal, but they don't resolve into anything obviously meaningful. It's not a simple repeated message like the prime numbers or pi that science fiction often imagines aliens might send. It's not images or audio that could be reconstructed. It's something else, complex waveforms that vary in ways that seem structured but don't match any encoding scheme humans use. One researcher suggests it might be a carrier signal, a framework designed to synchronize receiver systems before actual data transmission begins, like the handshake protocols computers use to establish connections. Another proposes it could be a beacon, a simple, repetitive signal meant to attract attention and confirm the object's artificial nature without conveying specific information. A third, more speculatively, suggests it might be status telemetry, the object reporting its condition to whoever might be listening, using a data format we don't understand because we don't know what parameters would be relevant to technology billions of years old. The SETI researchers brought into the project approach the signal with both excitement and extreme caution. They've spent careers searching for signals from the stars and finding nothing but noise and the occasional instrumental artifact. Now they have a genuine candidate, a signal from an object of unknown origin exhibiting behaviors consistent with artificial design, transmitting in the waterhole frequency range with structure that implies information content. It's exactly what they've been looking for, but decades of null results have made them skeptical, hyper-aware of how easy it is to see patterns in noise, how human brains are wired to find meaning even in randomness, so they apply the most rigorous tests, looking for every possible natural explanation before entertaining artificial ones. Could this be master emission, the radio equivalent of laser light, produced by molecules in the coma interacting with solar radiation? The spectrum doesn't quite fit, but with the right combination of molecules and excitation conditions, maybe. Could it be plasma oscillations in the coma, charged particles spiraling in magnetic fields and emitting radiation as they accelerate? The intensity seems wrong and the frequency stability is too high, but again, under exotic conditions maybe. The tests continue, each one eliminating some natural explanations but leaving others viable, and always the artificial hypothesis remains as the explanation of last resort, the one they'll accept only when everything else has been ruled out. And that's appropriate, that's how science should work, demanding extraordinary evidence before accepting extraordinary claims. But as the days count down and perihelion approaches, as the signal persists and strengthens and maintains its structured patterns despite all the changes in the object's environment, the sense grows that maybe, just maybe, this is the extraordinary evidence they've been waiting for. Maybe humanity's first confirmed contact with alien intelligence won't come as a radio message from the stars, but as a signal from an ancient artifact passing through our cosmic neighborhood, a messenger billions of years old finally delivering its message to someone capable of receiving it. The possibility transforms how people think about the next 2 weeks. This isn't just about studying an unusual comet anymore. It's about potentially answering the oldest question our species has ever asked. Are we alone? And if the answer is no, if 3I Atlas truly represents intelligence from beyond Earth, then what happens at perihelion might be the moment when humanity's perspective shifts irrevocably, when we stop being an isolated species wondering about our place in the cosmos and become instead the recipients of a message across time and space from minds that wondered the same things we wonder, in an age when our sun was young and Earth itself had not yet formed. 10 days to perihelion. The observation campaign reaches maximum intensity. Virtually every major telescope with a view of 3I Atlas is now dedicated to tracking it. The data flows in constantly, terabytes per day, processed by teams working in shifts around the clock. The electromagnetic pulses continue their shifted rhythm. The radio signal holds steady in power and frequency, the patterns within it resisting all attempts at decoding but clearly non-random by every statistical test applied. The core temperature rises as solar heating intensifies, but the hotspots remain distinct, their geometric patterns now stable, as if the system has reached some equilibrium state. The outgassing has increased dramatically, creating a coma bright enough that amateur astronomers with modest equipment can now see 3I Atlas as a faint smudge if they know exactly where to look. Photographs taken by enthusiasts around the world start appearing online, shared in forums and social media, often with excited speculation about what makes this comet special. The truth, the full scope of what professional observers are seeing, remains largely contained within scientific circles, but rumours leak, whispers that something unusual is happening, that this object might be more than it appears. NASA's communications team begins preparing multiple versions of the post-perihelion press conference materials. One version covers the scenario where 3I Atlas behaves normally, fragmenting or developing an enhanced coma, or simply passing perihelion without incident. That version emphasizes the scientific value of studying interstellar objects and presents whatever composition or structure data has been gathered as interesting, contributions to planetary science. Another version addresses the scenario where anomalies persist but remain ambiguous, where the observations don't resolve clearly into either natural or artificial explanations. That version is the hardest to write, because it requires conveying uncertainty without appearing evasive, admitting that we don't understand something without encouraging wild speculation. And there's a third version, the one that's been written and rewritten dozens of times, that addresses the scenario where the artificial hypothesis becomes untenable to deny. That version is simultaneously the most exciting and most terrifying document any of them have ever worked on, because it would mark the moment when humanity officially acknowledges that we're not alone in the universe, that intelligence has arisen elsewhere, and that one of its creations has come to visit us. The language has to be precise, neither overstating nor understating the implications. The tone has to balance wonder with rigour, enthusiasm with caution. Every word is chosen carefully because every word will be scrutinised and analysed and remembered. 5 days before perihelion, the trajectory calculations are refined to their highest precision yet, and a detail emerges that had been masked by earlier uncertainties. 3I Atlas's path through the inner solar system isn't just arbitrary. Its perihelion distance and the angle of approach are optimised for maximum solar radiation exposure, while minimising tidal stress from the sun's gravity. It's threading a needle, getting close enough to absorb substantial energy from the sun without getting so close that gravitational gradients would tear the structure apart. For a natural comet, perihelion distance is determined by whatever orbit the object happens to be on, the random result of whatever gravitational interactions ejected it from its home system. But 3I Atlas's perihelion sits right in the sweet spot, the distance where a technological object would want to operate if it were designed to use stellar energy for activation, or maintenance, or communication. This could still be coincidence, one more unlikely alignment in a series of unlikely alignments. Or it could be evidence of trajectory planning, of an object that was aimed precisely at this solar approach, billions of years ago by designers who understood orbital mechanics and stellar physics well enough to plot a course that would bring their creation through our sun's energy field at optimal parameters. The coincidences are piling up. Individually, each one might be dismissible. The rhythmic pulses could be natural resonance. The exotic isotopes could be coincidental formation environment. The controlled outgassing could be thermal processes we don't fully understand. The maintained rotation could be tidal locking effects. The radio emissions could be mass reactivity. The optimal perihelion could be selection bias. We only detected this object because its orbit brought it close enough to notice. But collectively, the weight of coincidence becomes harder to bear. At some point, the simpler explanation stops being that all these things happened by chance and starts being that they happened by design. That point is subjective, different for every scientist based on their prior beliefs and evidentiary standards. But as perihelion approaches, more researchers are crossing that threshold privately, if not publicly, reaching the personal conclusion that 3i Atlas is probably artificial even while maintaining official agnosticism until the data is absolutely conclusive. 3 days before perihelion, the sun's radiation has intensified to the point where the outer ice layers are sublimating rapidly, creating outgassing jets visible in high-resolution images as bright streamers extending from the nucleus. The jets aren't random. They fire from specific locations in coordinated sequences, creating a thrust pattern that, according to detailed dynamical analysis, is maintaining the object's rotation precisely despite the torques from asymmetric ice loss. It's an active stabilization system, whether natural or artificial, operating with a precision that seems almost impossible. The core is now hot enough that thermal imaging can map its structure in unprecedented detail, and what those maps show is geometry, not the random lumps and variations you'd expect from a natural object, but clean boundaries between regions of different temperature, straight lines and curves that look designed rather than accreted. Some researchers see spacecraft structure. Others see crystal formations or density variations in exotic ices. The debate rages in real time as new images arrive and are analysed by teams that haven't slept in days, running on coffee and adrenaline and the knowledge that history might be unfolding in the data they're processing. The radio signal strength peaks and then begins to drop, not because the source is weakening, but because the geometric alignment is changing, the object rotating so the antenna or whatever emits the signal is pointing away from Earth. The signal fades below detection threshold, and there's a moment of frustration, so close to perihelion, and we lose the radio data just when it might become most interesting. But 6 hours later, the signal returns, stronger than before, having completed a full rotation cycle and come back into view. And this time, something is different. The pattern has changed. The waveform that had been stable for weeks now shows new structure, additional frequency components, modulation that wasn't there before. It's still not decipherable, still not resolving into images or audio or any format we can interpret, but it's clearly a response to something, a change triggered by environmental conditions or internal programming, or just possibly by the approach of perihelion and the peak energy state that will enable whatever function this object was designed to perform. Perihelion arrives. At exactly 7 UTC, 3i Atlas reaches its closest approach to the Sun, 1.4 astronomical units, about 210 million kilometers from the solar surface. Every telescope is pointed, every receiver is recording. The data streams flow, and for 6 hours, as the object skims through perihelion and begins its outbound journey, humanity watches and waits to see what happens when an interstellar traveler, whether natural wonder or artificial messenger, encounters the full intensity of stellar radiation for perhaps the first time in millions of years. The outer ice layers are sublimating violently now, creating a coma that extends hundreds of thousands of kilometers, bright enough that it's briefly visible to the naked eye from dark sky locations as a faint star that wasn't there before. The jets fire continuously, dozens of them, creating a complex multi-tailed structure that shifts and changes as different vents activate and deactivate in sequences too rapid and too coordinated to track individually. The rotation rate increases, spinning faster as the thermal processes intensify, but the rotation axis remains stable, locked in place by forces we can measure but not fully explain. And the core responds. The electromagnetic pulses, steady for so long, suddenly accelerate, the frequency doubling and then doubling again, climbing through the radio spectrum into microwave ranges where fewer instruments can track them. The thermal patterns in the core shift, the hot spots merging and then fragmenting into new configurations, changing faster than the analysis software can process, creating a light show of temperature variations that looks almost like information being written and rewritten in heat. The radio signal peaks and then cuts off entirely, not fading gradually but stopping abruptly as if a switch has been thrown. And for 3 hours, silence. Nothing but the background noise of the cosmos while everyone watches and wonders if something broke, If the intense solar environment has damaged whatever system was transmitting, if we've just witnessed the death of the last functioning component of an artifact billions of years old, then the signal returns. Different frequency, different structure, broadcasting in a band that overlaps with the wavelengths our own deep space communication networks use. The coincidence seems almost too perfect, as if the object has been listening to our signals and chosen to reply using frequencies it knows we can receive. The waveform is complex, layered with multiple channels of information that might be redundancy encoding, or might be parallel data streams, or might be something else entirely that our communication theory doesn't account for. It transmits continuously for 47 minutes, an enormous data package by the standards of radio astronomy, and then stops as abruptly as it began. The object has passed through perihelion. Its outbound journey has commenced. The moment has passed, and recorded in receivers across Earth and in spacecraft throughout the solar system, captured in digital format ready for analysis, is what might be the first message humanity has ever received from beyond our own civilization, carried across the galaxy by a messenger that waited patiently through cosmic ages for the moment when it could finally deliver what it was sent to say. The analysis will take months. The press conference happens within hours, because the world's media has picked up on the unusual activity, the coordinated observations, the rumours leaking from research institutions. NASA's administrator stands at the podium, flanked by the directors of major observatories and the lead scientist from the investigation teams. The statement is carefully worded but unambiguous. 3i Atlas has exhibited behaviours and emitted signals that cannot currently be explained by natural processes. While no definitive determination can be made without further analysis, the possibility that this object represents technology of non-terrestrial origin must be seriously considered. The radio transmission recorded during perihelion is being analysed by teams worldwide. Results will be shared openly as understanding develops. A follow-up mission to intercept the object before it exits the solar system is under consideration. And regardless of what further analysis reveals, 3i Atlas has already taught us that the universe is more complex and possibly more populated than we knew, that our cosmic isolation may be less complete than we believed, and that the question of whether we're alone has moved from philosophical speculation to empirical investigation with data that demands explanation. The world reacts. Social media explodes with excitement and speculation and fear and wonder. Scientists worldwide request access to the data. Government agencies convene meetings to discuss implications and responses. Religious leaders offer interpretations. Skeptics demand rigour and caution. Believers claim vindication. And through it all, 3i Atlas continues its journey, moving outbound past Earth's orbit and toward the outer solar system, carrying its secrets with it, perhaps having delivered its message or perhaps having only begun a transmission that will require years to fully receive and decades to comprehend. The object will remain observable for months as it recedes, growing fainter but still trackable, still monitored by instruments that will watch for any additional signals or behaviours that might help decode what we've already received. And in laboratories and universities and space agency facilities around the world, the real work begins. The painstaking analysis of every scrap of data, the attempt to determine once and for all whether we've just made contact with intelligence from beyond Earth or witnessed the most elaborate natural phenomenon in recorded history. Either answer will change how we see ourselves and our place in the cosmos, but the direction of that change depends entirely on what the data ultimately reveals, and that revelation is still to come, still locked in waveforms and frequencies and patterns that might be information, or might be noise, or might be something we don't yet have concepts to understand, a message from a time and place so different from our own that bridging the gap will require us to expand not just our technology, but our thinking, developing new frameworks for comprehending what intelligence might look like when separated from us by billions of years and distances that light itself struggles to cross, but nevertheless reaching out, nevertheless making itself known, nevertheless proving that in this vast and ancient universe, the impulse to create and communicate and leave something lasting behind transcends any single world or species or epoch, and might be in the end as fundamental to the cosmos as gravity or light or time itself. The weeks following perihelion unfold in a strange mixture of frenzy and patience. The frenzy belongs to the media cycle, the public conversation, the endless speculation about what the transmission might mean, and whether humanity has truly received a message from another intelligence. The patience belongs to the scientists, who understand that answering those questions requires meticulous analysis that can't be rushed, that data doesn't reveal its secrets just because the world is watching and waiting. The transmission itself, that 47-minute burst of radio signal captured during perihelion, has been distributed to research institutions worldwide. It exists now as a massive file of digital samples, billions of data points representing the voltage fluctuations detected by receiver arrays as the signal washed over Earth. In raw form, it's meaningless, just numbers in a database. The challenge is extracting meaning if any meaning exists to be extracted. The first step is basic characterization. What are the signal's properties? The carrier frequency sits at 1612 MHz, right in the middle of the waterhole as expected. The bandwidth is narrow, only about 50 kHz, which suggests deliberate transmission rather than natural emission that would typically spread across a wider range. The signal strength varied during the transmission, not randomly but in patterns that repeat at different timescales, some fast oscillations occurring hundreds of times per second, and others slow variations that take minutes to complete a cycle. The polarization is circular, meaning the electromagnetic waves spiral as they propagate, and the direction of that spiral reverses at intervals that seem significant, though their meaning isn't immediately obvious. All of these characteristics are consistent with engineered signals rather than natural phenomena, but they don't by themselves prove artificial origin. Nature can produce surprisingly organized patterns under the right conditions. The next step is searching for structure. If this is a message, it should contain information, and information creates patterns that differ statistically from random noise. The researchers apply every test in the information theory playbook. They calculate the entropy, a measure of how unpredictable the signal is, and find it sits in an intermediate range, neither completely random nor completely predictable, exactly where you'd expect a data transmission to fall. They search for periodicities using Fourier analysis and find dozens of them at different frequencies, some strong and some weak, creating a complex rhythm that might be a timing structure for organizing the data. They look for repeated sequences, specific patterns that appear multiple times in the transmission, and find hundreds of them, suggesting either redundancy in coding to protect against transmission errors, or perhaps a vocabulary of symbols being used to build more complex structures. Every analysis points the same direction. This isn't noise, this is organized information. But organized how? And conveying what? The comparison to human communication systems proves both helpful and limiting. We know how we encode information for transmission. We use modulation schemes like amplitude modulation or frequency modulation, varying the strength or frequency of a carrier wave to encode data. We use error correction codes that add redundancy so receivers can detect and fix corruption. We use compression algorithms that remove redundancy to pack more information into less bandwidth. And we use framing structures that organize data into packets or blocks with headers and checksums. When the researchers look for these familiar patterns in the 3i Atlas transmission, they find hints of all of them, suggestions that maybe the encoding uses principles similar to ours, but the details don't quite match. It's like trying to read a book in a language that uses a familiar alphabet but unknown words and grammar. You can recognize that it's text, that it has structure and organization, but you can't extract the meaning without a dictionary and a grammar reference, and those don't exist for a language spoken billions of years ago on a world that might not exist anymore. One team takes a different approach. Instead of trying to decode the transmission as a whole, they look for segments that might be self-explanatory, portions of the message designed to teach the decoding method. This is the principle behind the Arecibo message that humanity sent toward the globular cluster M13 in 1974. A carefully designed transmission that started with simple mathematical concepts and built up to more complex information in a way that alien recipients might be able to decipher. If the 3i Atlas transmission follows similar logic, there should be a preamble, an introduction that establishes basic concepts and symbols before using them to convey more complex data. The search focuses on the first few minutes of the transmission, assuming that if a teaching section exists, it would come first. And there, buried in what initially looked like simple carrier wave variations, they find something extraordinary. A sequence that counts, a pattern of pulses that goes 1, 2, 3, 4, incrementing in a regular progression that any mathematical intelligence would recognize. It's the cosmic equivalent of saying, here's how to count in our system, now we can use these symbols to build more complex mathematics. The discovery electrifies the decoding effort because it provides a foothold, a starting point for understanding the rest of the transmission. If the opening section is a mathematical primer, then the subsequent sections might build on those foundations, using the established symbols and concepts to convey more sophisticated information. The team maps out what they believe is the structure, identifying transitions where the complexity level increases, where new symbols are introduced, where the transmission shifts from teaching fundamentals to transmitting actual data. It's painstaking work, requiring consensus among multiple researchers before any interpretation is accepted, but slowly a picture emerges. The transmission appears to contain multiple layers, starting with basic mathematics and physics, moving through chemistry and information about stellar environments, and culminating in something that might be astronomical data, positions and properties of stars as they were when the transmission was encoded. If this interpretation is correct, then 3i Atlas isn't just confirming its artificial origin. It's providing a map, a catalogue of its home region of the galaxy, as it existed in an epoch so ancient that most of those stars have evolved into different states or died completely. But even with this framework, huge sections of the transmission remain opaque. There are patterns that don't fit the mathematical progression, segments that seem to use completely different encoding schemes, portions that might be images or audio, or three-dimensional data structures or something we don't have concepts for. One particularly puzzling section near the end of the transmission shows regular oscillations at frequencies that correspond to nothing in the earlier portions, leading some researchers to suggest it might be instructions, a program meant to run on some kind of receiver device to reconstruct information that can't be transmitted directly. Another team proposes that the oscillations might represent temporal data, a timestamp indicating when the transmission was created using some absolute reference like the rotation period of the galaxy or the oscillation frequency of specific atomic transitions. Without knowing which interpretation is correct, both groups continue their analyses, building cases for their theories while remaining open to alternatives. The spectroscopic data from perihelion adds another dimension to the puzzle. When the outer ice layers sublimated violently during closest solar approach, materials from deeper in the structure were exposed, and the spectral signatures revealed composition details that had been hidden before. As expected, there were exotic isotopes, but the ratios between them told a story about formation conditions. The abundance of certain rare isotopes suggested creation in a supernova explosion, which makes sense for an old object from the outer reaches of the galaxy, where massive stars are more common. But there were also anomalies, isotopes present in ratios that don't match any single astrophysical process, as if the materials came from multiple sources and were somehow combined. Natural processes could explain this if the object formed in a region where multiple supernova remnants mixed together. But it could also suggest deliberate collection and assembly, gathering materials with specific nuclear properties for specific functions. The one isotope that generates the most discussion is a variant of osmium with an unusually high neutron count. This particular isotope is radioactive but with an extremely long half-life, decaying so slowly that a sample would take hundreds of billions of years to diminish significantly. And its decay produces a specific signature, a gamma-ray emission, at an energy that happens to be easily detectable by instruments designed to study cosmic ray backgrounds. If you wanted to create a long-lived power source that could be monitored remotely, that could signal its operational status across interstellar distances for billions of years, this isotope would be an excellent choice. Its presence in the core of 3i Atlas might be coincidental, just one of many exotic isotopes created in whatever stellar environment forged this object's material, or it might be intentional, a carefully chosen component of a system designed to operate and announce its operation over timescales that dwarf not just human civilization, but the lifespan of most stars. The trajectory analysis has been refined to incorporate every gravitational influence and non-gravitational force measured during 3i Atlas's passage through the inner solar system. When all the data is combined and the orbit is calculated with maximum precision, something remarkable emerges. The object's trajectory through our solar system isn't a random hyperbolic path determined by whatever velocity it happened to have when entering our gravitational neighbourhood. It's optimal in a very specific way. The path maximizes observation opportunities, bringing the object close enough to every major planet for detailed gravitational measurements while maintaining safe distances that prevent catastrophic tidal disruption. It's exactly the route a survey mission would choose if the goal were to characterize our solar system's mass distribution and planetary architecture. The probability of achieving this trajectory through random chance is vanishingly small, small enough that it strains credibility to attribute it to coincidence. Some scientists argue that this optimization could emerge naturally through a selection effect. Perhaps many interstellar objects pass through our solar system on random trajectories, but we only detect the ones that happen to come close to Earth and the Sun, where our instruments are concentrated. In that case, the objects we see would naturally tend to be on trajectories that bring them into the inner solar system, creating an illusion of intentional targeting. It's a valid point, and it's the kind of alternative explanation that must be considered before accepting more extraordinary interpretations. But the counter-argument is equally compelling. 3I Atlas wasn't detected by chance observation. It was found by a systematic survey designed to discover exactly these kinds of objects. And if its trajectory were simply one of many random paths, the optimization for planetary encounters would still require explanation. Natural selection doesn't operate on trajectories the way it operates on organisms, so the mechanism by which random paths would preferentially produce this specific optimization remains unclear. The debate continues in academic journals and conference presentations, with researchers on both sides publishing papers that support their interpretations and critique the alternatives. This is science functioning as it should, multiple hypotheses competing based on evidence and logical argument, with the community gradually converging toward whichever explanation best accounts for all observations. The process is slow and sometimes contentious, but it's the only reliable path to understanding. And while the debate unfolds, 3I Atlas continues its journey outward, now beyond Earth's orbit and headed toward the asteroid belt, still observable but growing fainter as the distance increases and the solar heating that powered the intense perihelion activity diminishes. The electromagnetic pulses have returned to their pre-perihelion rhythm, the shifted frequency becoming the new normal. The radio emissions have ceased entirely, no further transmissions detected despite continuous monitoring by facilities around the world. Whatever the object had to say, it apparently said during that 47-minute window, and now it has returned to silence. Plans for an intercept mission have advanced from preliminary concepts to serious engineering proposals. Multiple space agencies have contributed designs, and international cooperation agreements are being negotiated to pool resources and expertise. The mission architecture that's emerged as most feasible involves a small spacecraft, maybe 500 kilograms total mass, launched on a trajectory that uses Earth's gravity for acceleration, and then deploys a solar sail to build up the enormous velocity needed to catch 3I Atlas before it exits the solar system. The spacecraft would carry a suite of instruments, cameras to image the surface at close range, spectrometers to analyze composition in detail, magnetometers to map any magnetic fields, and particle detectors to measure the radiation environment around the object. If the budget allows, there might even be a small lander, a probe that could touch down on the surface and drill a few centimeters into the ice to collect samples for analysis. The timeline is tight. 3I Atlas is moving at roughly 20 kilometers per second relative to the Sun, and every day of delay means the object is another 1.7 million kilometers farther away, making intercept more difficult and expensive. The mission would need to launch within 18 months to have any realistic chance of success, which means design and construction would have to proceed on an accelerated schedule with minimal time for the usual testing and validation that reduces risk. The cost estimates range from $2 to $5 billion depending on which capabilities are included, a substantial investment but not unprecedented for missions considered scientifically valuable. The question is whether the potential return justifies the expense. If 3I Atlas is natural, even if unusually so, the scientific value of close-up observations might not warrant the cost, when that money could fund multiple smaller missions to other targets. But if there's any chance the object is artificial, if there's any possibility that we could study technology from another civilization, then the value becomes almost incalculable, worth almost any cost because the knowledge gained would transform our understanding of our place in the universe. The decision will be made at the political level, by space agency administrators and government officials who must weigh scientific priorities against budget constraints and public interest. The scientists can provide recommendations, can argue for the mission's value, but they can't unilaterally commit the resources needed. And so there's lobbying, public outreach, efforts to build support for the mission among policymakers and the general public. The researchers who've spent months studying 3i Atlas give presentations, write op-eds, appear on news programs, explaining what they've learned and why the questions that remain deserve answers that can only come from a dedicated mission. Some emphasize the scientific value, the opportunity to study interstellar material and exotic ices, and potentially resolve the question of artificial origin definitively. Others emphasize the inspirational aspect, the chance to demonstrate humanity's capability and curiosity, to show that we can respond when the universe presents us with something extraordinary. Public opinion is divided, as it always is on ambitious space projects. Supporters argue that exploration and discovery are fundamental human drives, that answering deep questions about our cosmic context justifies significant investment, and that the technological spin-offs from such missions often prove valuable in unexpected ways. Critics argue that the money would be better spent on problems here on Earth, that space exploration is a luxury we can't afford when there are pressing needs for healthcare, education, and infrastructure, and that the likelihood of finding definitive proof of artificial origin is too low to justify the expense. The debate plays out in comment sections and call-in shows and letters to representatives, a democratic process determining whether humanity will rise to meet this particular challenge or let the opportunity slip away. Meanwhile, the analysis of the perihelion transmission continues, and new discoveries emerge from the data. One team focuses on the timing structure, the patterns of when pulses occur and how long they last, and finds what might be a coordinate system. If the timing intervals represent angles and distances using mathematical relationships established in the opening section of the transmission, then the entire message might be a catalogue of positions, a map of something displayed in a format that uses time rather than spatial dimensions. It's an unusual way to encode spatial information, but for a radio transmission where time is the fundamental dimension and space must be inferred, it might be the most natural approach. The team begins the laborious process of converting the timing patterns into three-dimensional coordinates, building a point cloud that might represent stars or planets or something else entirely. What emerges is both fascinating and frustrating. The points definitely form structures, clusters and filaments and voids that look like cosmic large-scale structure, the distribution of matter across galactic scales. But the scale is wrong. If these are stars, they're distributed across a region hundreds of light-years across, far too large for a single stellar neighbourhood, but too small for an entire galaxy. If they're galaxies, the number is too small and the clustering too tight. The interpretation that best fits is that this represents a specific region of space, perhaps the volume surrounding 3i Atlas's origin point, mapped at a time when the transmission was created. If so, then this is literally a map showing us where the object came from, providing coordinates that could, in principle, allow us to identify the home system, or at least narrow down the search region. The problem is that stars move. Over millions or billions of years, stellar positions change significantly due to orbital motion around the galactic center and random velocities from gravitational interactions. Without knowing when the map was created, matching it to current stellar positions is nearly impossible. But there's a potential solution. If the map includes not just positions but also velocities, information about how fast each point is moving, then the data contains enough information to run the stellar motions backward in time and see where the stars were in the past. This is standard practice in galactic archaeology, the study of stellar populations and their evolution, and the techniques are well established. The challenge is extracting velocity information from the transmission, which requires identifying which portions of the data encode that information and how the encoding works. Multiple groups are working on this problem, trying different assumptions about the data structure, testing whether their interpretations produce results that make physical sense. It's slow going, and many attempts lead to nonsensical results. Velocity fields that would require physics, violating energy sources or produce stellar distributions that don't match what we know about galactic structure. But occasionally, someone tries a particular interpretation and gets results that look plausible. Stellar motions that could be real, and those cases get added to a growing collection of partial solutions that might eventually combine into a complete answer. There's also the question of what else might be in the transmission besides astronomical data. Some researchers believe they've identified sections that could be images, two-dimensional data arrays that might represent visual information. The challenge is figuring out the resolution and color encoding. Without knowing how many pixels across the images are supposed to be, or how many bits encode each pixel's brightness and colour, you can't reconstruct the image meaningfully. You end up with noise or garbled patterns that might or might not be the intended result. One particularly dedicated team has been trying every possible combination of resolution and bit depth, generating thousands of candidate images and examining them for anything that looks like intentional structure rather than random artifacts. Most attempts produce static, but occasionally something emerges that looks almost meaningful, hints of edges or gradients or patterns that seem too regular to be chance, and those get flagged for further analysis and cross-checking with other teams to see if independent approaches converge on similar results. The most speculative interpretation comes from a group of researchers with backgrounds in archaeology and anthropology who approach the transmission not as a technical data package, but as a cultural artifact. They argue that any message sent across interstellar distances by a civilization sufficiently advanced to engineer such a transmission would include not just dry factual information, but also context, cultural meaning, perhaps even artistic expression. They look for sections of the transmission that don't fit technical encoding schemes, portions that might be poetry or music or visual art, attempts to convey something about the civilization's values and aesthetics and ways of understanding the universe. It's a beautiful idea, the notion that 3i Atlas might carry not just data but also a piece of the soul of whoever sent it, a glimpse into how another intelligence experiences existence. But it's also nearly impossible to validate, scientifically. How do you prove that a particular pattern represents art rather than just an encoding scheme you haven't figured out yet? How do you distinguish meaningful cultural content from random noise or misinterpreted technical data? The team tries anyway, applying techniques from semiotics and structural analysis, looking for patterns that might indicate symbolic representation or metaphorical meaning. They find sections of the transmission that show what might be hierarchical structure, organization into nested levels that could represent categorization or relationships. They find repetitions that might be emphasis, specific patterns that appear multiple times as if highlighting their importance. They find variations on themes, basic structures that get elaborated in different ways, creating a sense of development or exploration. Whether any of this represents genuine cultural content or is just the result of their interpretive frameworks, imposing meaning on ambiguity remains an open question, but the very attempt is valuable because it acknowledges that intelligence and communication involve more than just information transfer, that meaning exists at multiple levels, and understanding requires engaging with all of them. As the months pass and 3i Atlas recedes farther from the Sun, the observation intensity gradually decreases. There are only so many telescopes and only so much time, and other scientific priorities need attention too. The continuous monitoring gives way to periodic check-ins, scheduled observations to confirm the object is still on its predicted trajectory and to look for any late-stage activity or surprises. The data collection shifts from raw observations to analysis of what's already been gathered, the focus moving from accumulating more data to extracting meaning from what exists. This is a natural progression in any observational campaign, the transition from discovery phase to interpretation phase, but it comes with a melancholy awareness that the window is closing. 3i Atlas will remain observable for another year perhaps, growing fainter until it crosses the threshold where only the largest telescopes can detect it, and then it will fade completely, disappearing into the cosmic darkness from which it emerged, leaving us with only the data we managed to gather during its brief passage through our neighbourhood. The question of what we've actually learned from 3i Atlas remains contentious. The conservative position holds that while the object exhibits unusual properties and behaviours, none of them definitively prove artificial origin. Every anomaly might have a natural explanation even if we haven't identified that explanation yet. The radio transmission, as complex as it is, might be a natural phenomenon produced by conditions we don't fully understand, some combination of plasma processes and electromagnetic dynamics in the coma that creates structured emissions through mechanisms that happen to mimic designed signals. The orbital optimization might be selection bias or coincidence. The geometric structures in the thermal maps might be crystal formations or density variations in exotic ices. Until we have proof that categorically rules out all natural explanations, the hypothesis of artificial origin remains speculative, an interesting possibility but not a confirmed fact. This position is intellectually honest and scientifically rigorous, refusing to make extraordinary claims without extraordinary evidence. The opposing position argues that waiting for absolute proof is setting an impossible standard. We'll never have certainty unless we directly examine the object and find unambiguous artifacts like manufactured components or inscribed messages. Barring that kind of direct evidence, we have to make judgments based on the balance of probabilities, asking which explanation, natural or artificial, requires fewer unlikely assumptions and better accounts for the totality of observations. By that standard, the artificial hypothesis performs well. It explains the electromagnetic pulses, the controlled outgassing, the optimal trajectory, the structured radio transmission, all with a single assumption, that 3i Atlas was designed by intelligence. The natural explanation requires multiple separate assumptions, each individually unlikely, to account for the same observations. At some point, applying Occam's razor, the simpler explanation is the one that invokes design rather than piling coincidence upon coincidence. This position is also intellectually honest, acknowledging uncertainty while arguing that the available evidence tips the scales toward artificial origin even without absolute proof. The debate reflects deeper questions about scientific methodology and evidentiary standards. How much proof is enough? When does a hypothesis graduate from interesting speculation to accepted theory? Different fields have different standards, and there's no universal answer. In particle physics, the standard for announcing a discovery is 5 sigma, a statistical threshold that means the probability of the result being due to chance is less than 1 in 3.5 million. In astronomy, standards are often more flexible, with significant discoveries accepted based on multiple independent observations that converge on consistent results, even if no single observation crosses a strict statistical threshold. For something as unprecedented as potential evidence of extraterrestrial technology, what should the standard be? Should we demand overwhelming proof before accepting such an extraordinary claim? Or should we embrace the uncertainty and accept that the question might not have a definitive answer, that we might have to live with ambiguity and adjust our beliefs provisionally based on the best available evidence? These questions have practical implications for how resources are allocated and decisions are made. If we're confident 3i Atlas is artificial, then the intercept mission becomes a top priority, worth significant investment and risk. If we're uncertain, the calculus changes, and the mission competes on more equal footing with other scientific priorities. The decision-makers responsible for these choices would love to have clarity, a simple yes or no answer from the scientific community about whether 3i Atlas represents technology from another civilization. But science doesn't always provide simple answers, especially at the frontiers where we're investigating things we've never encountered before. The honest answer is that we don't know for certain, that the evidence is consistent with artificial origin but doesn't prove it definitively, and that reasonable scientists examining the same data can reach different conclusions based on different assumptions and standards. That ambiguity is uncomfortable, but it's also the reality of working at the edge of knowledge, where certainty is rare and provisional understanding is the best we can achieve, and so the community moves forward with that uncertainty, continuing to analyze the data, publish papers arguing different interpretations, hold conferences where the debates are aired and evidence is examined from every angle. The process is messy and sometimes contentious, but it's how science advances when confronting genuinely novel phenomena. Consensus will emerge eventually as more evidence accumulates, and some explanations prove more robust than others. But that emergence takes time, sometimes years or even decades, and in the meantime the uncertainty persists. For those of us watching the process unfold, the temptation is to demand answers, to insist that the scientists tell us definitively what 3i Atlas is. But that demand is unreasonable if the data doesn't support definitive conclusions. The more honest response is to accept the uncertainty, to appreciate that we're witnessing a genuine scientific mystery in real time, and to trust that the process of investigation will eventually lead to understanding, even if that understanding comes slowly and incompletely. 3i Atlas has changed how we think about interstellar objects and what they might represent. Before its discovery, the assumption was that visitors from other stellar systems would be simple, passive chunks of rock or ice, fragments ejected from planetary systems during formation, wandering the galaxy until chance brings them near another star. That picture was always provisional, based on the few examples we'd observed, but it felt reasonable. Now we know that interstellar objects can be complex, can exhibit behaviors that challenge our categorization schemes, can carry information, or at least structures that look like information. Whether that complexity emerges from exotic natural processes or from intelligent design, it expands the envelope of what's possible, what we should expect when the next interstellar visitor arrives. And there will be next visitors. Our detection capabilities are improving, survey telescopes are coming online that will find objects earlier and track them more completely, and statistical models predict we should discover multiple interstellar objects per year once these systems are fully operational. Each new object will be an opportunity to test our understanding, to see if 3i Atlas was unique or representative of a broader category. The legacy of 3i Atlas will be measured not just by what we learned from this specific object, but by how it changed our approach to studying such objects in the future. Observation protocols have been updated to include searches for electromagnetic emissions and controlled outgassing patterns, things that weren't considered priorities before, but now seem essential for characterizing interstellar visitors completely. Data analysis techniques have been refined, with new algorithms developed specifically for detecting structured signals in complex datasets. International cooperation frameworks have been strengthened, with space agencies around the world coordinating more effectively to ensure that resources are deployed efficiently and that data is shared openly. These improvements will benefit all future studies, regardless of whether we ever find another object as enigmatic as 3i Atlas. There's also a human legacy, the impact on how people think about the cosmos and our place in it. For many who follow the story of 3i Atlas, it was a reminder that the universe is vast and old, and full of possibilities we're only beginning to explore. The idea that an object from another stellar system could carry a message across billions of years, that intelligence might exist on timescales and distance scales that dwarf human experience, that we might be part of a broader cosmic story involving other minds and other civilizations, these ideas capture imaginations in ways that purely technical astronomy sometimes doesn't. Even if 3i Atlas ultimately proves to be natural, even if the message interpretation turns out to be wishful thinking and pattern recognition run amok, the object has served a valuable function by making the universe feel more alive, more connected, more meaningful than a purely mechanical view might suggest. The final observations of 3i Atlas are scheduled for late 2026, nearly 2 years after discovery, when the object will have receded to the point where even the largest telescopes can barely detect it. Those final images will likely show nothing more than a faint point of light, all detail lost to distance, but they'll mark the end of an era, the conclusion of humanity's first extended study of an interstellar visitor that challenged our assumptions and expanded our questions. What comes after depends on decisions being made now, on whether the intercept mission receives funding and approval, on whether new analytical techniques succeed in extracting more information from the perihelion transmission, on whether the next interstellar object discovered exhibits similar mysteries or proves to be more mundane. The story of 3i Atlas isn't over, not yet, but it's entering a new phase where the focus shifts from observation to interpretation, from gathering data to understanding meaning. And in the end, maybe that's the most profound lesson 3i Atlas offers. Understanding doesn't come easily or quickly when confronting the genuinely unknown. It requires patience, rigor, willingness to live with uncertainty, and openness to possibilities that challenge our existing frameworks. It requires both skepticism to avoid being fooled by our own wishful thinking and imagination, to consider alternatives we might not have thought of before. It requires collaboration, bringing together different perspectives and expertise to examine questions from multiple angles. These are the skills and attitudes that allow science to advance, that enable humanity to learn about the universe and our place in it. 3i Atlas has been a masterclass in how that process works, and regardless of what conclusions we ultimately reach about the object's nature and origin, the experience of studying it has made us better at asking questions and seeking answers. The universe will keep presenting us with mysteries. Some will be explicable through known physics and chemistry, natural phenomena we haven't encountered before but that fit comfortably within our theoretical frameworks. Others will be truly puzzling, pushing the boundaries of what we thought was possible, forcing us to expand our theories or develop new ones. And occasionally, perhaps very occasionally, we might find something that doesn't fit any natural explanation, something that points toward intelligence and technology from beyond Earth. Confirmation that we're not alone in the cosmos. 3i Atlas might be that confirmation, or it might not. But either way, it's taught us how to look, what to measure, what questions to ask when the next candidate appears, and it's reminded us that the search for understanding is itself valuable, that the journey matters as much as the destination, and that the universe rewards curiosity with wonders that exceed our capacity to predict or imagine. So we continue watching, continue analysing, continue debating and investigating and pushing toward answers, even when those answers remain frustratingly elusive. The electromagnetic pulses from 3i Atlas's core still echo in the data, steady and mysterious. The perihelion transmission still waits in databases, its secrets partially revealed but not fully decoded. The object itself continues its journey, carrying whatever truths it contains farther into the cosmic darkness with each passing day. And we remain here, on this small planet orbiting an ordinary star, looking up and wondering and working to understand, driven by the ancient human impulse to know what's out there and what it means that we exist to ask the question. That impulse, that drive to explore and comprehend, might be the most fundamentally alive thing about us. It transcends individuals and generations, connecting us to everyone who came before, who looked up at the night sky and wondered, and to everyone who will come after who'll build on what we learned. 3i Atlas, in its way, represents the same impulse expressed across unimaginable distances and time spans. If it's natural, it shows how the universe creates complexity and structure without intention, a reminder that physics alone can produce wonders. If it's artificial, it shows that the drive to explore and communicate and reach out might be universal, shared by any intelligence that arises anywhere in the cosmos. Either way, it's a mirror, showing us our own curiosity reflected back across the void, inviting us to keep questioning, keep searching, keep reaching toward understanding, even when the answers hide behind layers of uncertainty and distance. And in that invitation, in that call to continue the journey of discovery, lies the real meaning of what 3i Atlas has brought us. A gift not of answers, but of better questions, and the inspiration to keep pursuing them no matter how difficult the path becomes.